Okay, everyone, let's get started. So we're going to just continue with where we left off on yesterday. And so if you remember yesterday, we discussed how BERT works, and we discussed how you actually use BERT to solve a text classification task. So today we're going to, maybe I'll keep these over here. Today we're going to go a little further and see how we can apply BERT to solve sentence pair classification, or any general task where you have two pieces of text as an input and you're asked to judge some relationship between those two sentences. We will also look at question answering and solving question answering using BERT. A specific type of question answering called reading comprehension or extractive question answering. Towards the end of the lecture, we will also cover advanced variants of BERT that improve upon it in certain ways, but all of them share the general backbone, this masked language model that we talked about in the last class. I'll also add that I posted on Piazza yesterday, there's an interesting NLP related talk right after this class at 4 p.m. I posted the Zoom link so all of you can attend. I actually have to introduce the speaker, so I'll try and end this class a little bit early so I can make it back to my office in time. So yeah, but we still have a lot of stuff to cover. Yeah, anything else? Any logistics or admin related questions? Your homework 0 grades were posted on Gradescope, so you can take a look at those. If you disagree with anything, you can submit a regrade request, and the graders will determine if you'll be awarded extra points or not. So, but the grades were generally really good. All right, no questions? Okay, let's get started. So I wanted to start with just a review of the high-level pre-train and fine-tune process that we talked about in the last class, just so that we're all on the same page, and then we'll go from there. So remember that we had two phases, right? We had pre-training, in which I took an input sequence. And so in BERT, this sequence is of length 512 tokens. So it's not just a short sentence or phrase like in our examples, it's actually maybe a paragraph long. And you mask out some percentage of the tokens at random. So in the original BERT paper, this was set to 15%. I posted the paper we were discussing in the last class on the website, where just a couple weeks ago, some researchers showed that masking 40% can actually lead to better performance, so you can check that out if you're interested. But in the pre-training phase, you generally mask out some percentage of the tokens, you feed the input with the mask token into BERT, and BERT is, of course, a transformer encoder. So remember, last week we talked about all the different types of transformer variants, like encoder only, decoder only, encoder, decoder, prefix LM. BERT is an encoder only model, meaning that it has fully unmasked self-attention at every block. So no masking going on. And the reason why we can get away with no masking is because the things that we're trying to predict do not occur anywhere in the input, right? We're trying to predict what goes into this mask token. It's not given to us in our input. So the model is free to use any information in this sequence to predict the identity of this mask token. We don't need to actually mask out future words or anything like that. This is the masked language modeling objective. So then we get as output like these 5 vectors, and our mask token we're going to predict opened, And remember, last class we discussed this special CLS token that is prepended to every input. So this is also prepended during pre-training. So we have this CLS token, it's never masked, and we get a final layer representation for this token too. So this was the pre-training phase, right? So we can pre-train this BERT model for as many iterations on as much data as we can acquire, since the labels come for free here. So remember, our definition of pre-training was we train the model from scratch using a self-supervised objective, which is one where the labels just come from free from like large amounts of text. So language modeling or masked language modeling are examples of this task. And we are able to train this model on as much data as we can, so our model can actually be very big as well. So we can train a very deep and big transformer model for the task of masked language modeling. And then, once we've accomplished that, we get to the fine-tuning process, which we talked about towards the end of the last class for text classification, right? So we were using the example of sentiment, where you might have an input like this movie is good. And so if this is our BERT model, we pre-train it and we get this model that's colored in orange. Now we're going to use the exact same model to initialize this sentiment BERT model. And all of these words get input into BERT, and we, as usual, get the vectors corresponding to each token as our output. And on top of the vector associated with this CLS token, we're going to add a new softmax layer to predict positive, right? So in this process, this softmax layer trained from scratch. So we do not take the softmax layer from our pre-trained model, the one that's predicting opened up here, right? Because that's doing a completely different classification task with many, many more labels. Instead here, we just add a new softmax layer on top of this pre-trained BERT to predict the sentiment labels. So one distinction to make is that the data in the pre-training phase comes from huge volumes of unlabeled text, right? So I don't need sentiment reviews for the pre-training phase, right? I just need any sort of text. However, in the fine-tuning phase, my data comes from labeled reviews. That's for sentiment analysis, right? If you're doing document classification, you'd need some labeled documents or something like that with the topic labels. So this is for sentiment. Okay, and during the fine-tuning process, we do the backprop not only into the new softmax layer that we've created for a sentiment, but also into the entire BERT model, right? So into all the layers, all the parameters of the pre-trained model are being adjusted to do a better job at the sentiment analysis task. So finally, we talked about terminology in our last class. The downstream task is another phrase that I mentioned quite frequently in the last class, and some of you were confused about what that meant. So broadly, the downstream task is the one that we actually care about solving. So if I were a company I might care about getting a better review sentiment predictor, right? I don't actually care about getting a great masked language model that doesn't solve any of the use cases for my company. But the fact that I can pre-train and then fine-tune increases my performance on the sentiment data set. So the downstream task in this example is, sentiment analysis. This is usually the task that we are fine-tuning our model on. This can be contrasted with the pre-training task, which in this case is masked language modeling. So again, our goal is not to solve masked language modeling. Our goal is to get a better sentiment classifier, which is our downstream task. So to get the best possible performance on our sentiment task, we find that pre-training and then fine-tuning gives us a much higher performance than training a model from scratch on the labeled data. So basically, if I cut out this pre-training phase and I only do fine-tuning from scratch on the downstream sentiment data, I do much worse. And at the end of this lecture, we'll look at some actual numbers, like results on a bunch of different tasks from the BERT paper. You can also check those out just to see what the difference is by adding pre-training versus not having it. All right, so any questions about this? This is generally a review. Yeah?
So, in the last step, when it first gets the actual sentiment, the softmax layer creates a probability distribution only over like 2 different possibilities.
Yeah, that's right. So the question is, this new softmax layer that we add in the fine-tuning process, wow, I don't even know what I'm doing. This softmax layer projects that final CLS representation into a 2D vector. So there are 2 classes, right? Positive or negative. Or it could be, 3 classes if neutral is considered. But yeah, this is a new softmax weight matrix compared to the one used in pre-training. All right, any other questions? No questions on YouTube? Okay, so let's switch gears then to a different task. So we've talked about text classification now. Let's switch over to sentence pair classification. So this is also a task that can be of interest to many people. Sentence pair. So here I have 2 sentences, S1 and S2, and I'm interested in some sort of relationship between these 2 sentences. So one of the canonical tasks of this pairwise classification is NLI, which stands for Natural Language Inference, and it's also referred to as textual entailment. And so in this task, I'm given 2 sentences, S1 and S2, and a model must figure out if S2 either entails, contradicts, or is neutral towards S1. So entailment, so if S2 entails S1, it basically means that this sentence S2 is true given whatever is said in S1. If contradicts, it means that S1 is false given whatever is said in S1. And neutral means you cannot make any truth judgment about S2 given S1. So as an example, take S1 equals the dog walks, S2 is the dog sits still. Here, these two are in contradiction, right? Because in the first sentence, the dog is moving, the second sentence, the dog is not. However, if S2 was the dog is moving, then this would be an entailment. If S2 was, the alien is sleeping, then these two would be neutral, right? Because it doesn't say anything about an alien in sentence 1. So there are two labeled data sets for this task. These are SNLI and MNLI. I mean, there are a whole lot more, but these are the two most prominent ones in the literature. These consist of, on the order of 100,000 or 200,000 pairs of sentences, along with the label, entailment, contradiction, or neutral for each of them. So this task, initially people solved via just the standard, take a model, initialize it from scratch, initialize it randomly, and then train it from scratch on these data sets. But of course, we know that, this pre-train and fine-tune paradigm is much more powerful than training a model on only labeled data. And so when BERT came around, it set like huge gains on these kinds of tasks. One complication, perhaps, is that these tasks actually involve two sentences, not one. So how do I get my BERT model to do this? Otherwise, this is the same as a text classification task, right? I have 3 labels and I have some input. I want to do a classification task. So the way in which you solve this is very simple. Basically, given these 2 sentences, I'm going to put them into BERT. I put the first sentence, the dog walks, and then I use a special token, which is part of BERT's vocabulary, called the separator token. And then the dog sits still. So this token here, the separator token, is a special token in BERT vocab to be used to separate distinct parts of the input from each other. So now that I have this input sequence, it's very straightforward, right, to treat this as a text classification task. I get all of these different vectors as output, right? I have one for my CLS, one for dog, blah, blah, blah. I have a lot of these final layer vectors. I will just put a new softmax layer for 3-way classification on top of the CLS vector, predict contradiction here. So nothing too fancy, but this is a technique you can use when you're interested in inputs that have, when each example has multiple different pieces of text input. You can kind of just concatenate them together using the special separator token and treat it as a classification problem. Okay, so any questions about this? You can also use this same setup for things like paraphrase, identification, and other pairwise tasks. Yeah?
What would we mean by backpropagating into the separator token?
Okay, the question is, what does it mean to backpropagate into the separator token? So think about what the separator token's purpose is. The model basically has to have some representation of the first sentence and some representation of the second sentence, right? And then it has to do some sort of evaluation of these 2 representations in order to decide if the sentences are in an entailment or contradiction relationship, right? So the backprop into the separator token and into the rest of the model will hopefully tell BERT that, look, everything before the separator token should be treated as one, piece of meaning. Everything after should be treated as a separate thing, and then you should do some sort of matching of these vectors in the higher level layers. Of course, we don't actually know what is going on in this process, but the fact that this works very, very well indicates that the model is actually learning to use the separator token in this way to demarcate the boundaries of the two sentences. Other questions? Yeah. Yeah, so in the original BERT paper, they had this, all of their inputs had two distinct segments, and they had a classification task called next sentence prediction over the CLS token. We didn't talk about that here because it doesn't actually, it's not necessary for this whole process. So if you have a task that requires more than two different inputs, you could just concatenate them using multiple separator tokens, and it will probably work. So remember that the separator token here, even though you might add, another separator token and then another sentence after this for whatever task you care about, note that those two separator tokens will be distinguished from each other via the position embeddings. So it's not like the model will be confused. It will know that there are different separator tokens in the sentence. All right, let me on YouTube. Does the mask token have a learned embedding like any other token, or is it something like a vector of all zeros? So the mask token has its own learned embedding. That embedding is also pre-trained, right? It's critical during the pre-training process to use this mask token. So it's not a vector of all zeros. It's just treated as any other embedding in the vocabulary. All right, let's go back to, what was I doing? All right, so now let's get to a more complicated task. We'll switch from classification, or kind of this like sequence level or in pairwise sequence level classification to question answering. So you can see how to use the same setup to solve a different task. So BERT for extractive question answering. So what extractive means is that in this setup, you're given a passage, like a paragraph or a document, and you're given a question about that document, and it's guaranteed, at least in the initial data sets, that the answer to the question is some span of text within that document. So this is a pretty restrictive QA setup, right? It doesn't consider the case where the answer is outside of the document, or when the answer cannot be expressed as some span from the document but needs to be summarized or simplified or something like that. But nevertheless, it's an easy way to set up an initial QA task that you can then make more complex. So to formalize this task a little bit, your input is a question and a passage. And in the initial extractive QA data sets, these passages are usually pretty short, like a paragraph from Wikipedia is generally the size of passage that we're talking about here. And our goal is to predict a contiguous span of text from the passage that answers the question. So some example data sets here are SQUAD, the Stanford question answering data set, Quack, which is one I helped to develop, that is basically this format in conversational form. There's things like COCA, there are other data sets using this format, HotPot QA, many others. There's probably like hundreds of these kinds of data sets at this point. So it's important to learn about them, and then later on in the semester we'll talk about the limitations of the setup and other more flexible question answering paradigms. But as an example here, you might get a question like, who starred in the Matrix as Neo? So you might have a question like this, and you might have a passage from Wikipedia, from the Wikipedia article about the movie The Matrix, so it has some words, you know, blah, blah, blah. And then at some point it says, you know, Neo was played by actor Keanu Reeves, and it has more text here. So the goal of this model is to basically extract this span that corresponds to the answer of the question from the passage. And specifically, the model produces an index, a pair of indices, I, J, which correspond to the positions of these words in the input paragraph. So if this is position 1, 2, 3, so on, maybe this one is I, and this one is J, and the model returns these two indices. Okay, is that clear? All right, so let's take a look at how we actually use BERT to solve this extractive QA problem. As before, we're going to make use of the special tokens that we've seen up till this point. This is the first task where the CLS token is not the one in which we're putting our classification head over. So here, note that we are interested in finding a span of text in the passage. We're not interested in like putting a softmax layer over this passage to predict one answer out of many possible answers, right? That's just not feasible given how many possible questions and answers there could be in this kind of setup. So instead, we're going to first formulate our input sequence, like we have the CLS token, we have the question, who starred in the Matrix, and then we have our separator token, which we saw from the previous task of sentence pair classification. Here it's used to separate the question text from the passage text. So the model should learn that none of these vectors associated with the question words can be part of the, or can form the answer, right? The index should come from after the separator token. So here we might have, you know, some words of the passage, and then eventually we get to Keanu Reeves, and we have another word, and so on. So, right, we have a lot of words of our passage, and our goal is to put this thing through BERT. Again, we are just going to, like in all of the previous cases, use the pre-trained BERT model to start with, and then fine-tune this model using our QA task signal. These data sets like Squad and so on have on the order, again, of 100,000 examples of questions paired with passages and answers. So it's a fairly large data set. And at the end of this, we get all of these vectors, right? So we get vectors for the CLS token, all these question words, but the ones we're actually interested in are after the separator tokens, so the passage tokens. So I might get a vector for P1, a vector for P2, a vector for P3, a vector for Keanu Reeves, and then this last passage token that I've shown in this example. And now I have to figure out how to actually extract this answer. So the way in which BERT does this is we set up two different softmax layers for classification, and we apply them to all of the token level representations in the final layer of the, all of the passage token representations in the final layer. So all of these. So if we say that, you know, these are passage tokens, these are the vectors associated with those tokens, and we're going to put two different classifiers on each one. So we have two binary classifiers, and the first classifier, and these are implemented with softmax layers. The first one predicts whether the token is the start of the answer, and the second predicts whether it is the end of the answer. So basically, we are predicting, we have a classifier to predict one end of the span boundary and the other end of the span boundary. Let me move this up so I have some space to draw these things. Over here. Okay, so let's say that we're going to color one of these in red and one of these in blue. So for every passage token, I'm going to have my first classifier predict 0 or 1. Is this the start of the answer span or not? So here, this is 0. This representation corresponds to Keanu Reeves. Keanu. So I'm going to predict 1 here and then 0 everywhere else. And just like this, I'm going to do the same thing for my end of answer span classifier. So this is going to predict 0 everywhere, predict 0 for Keanu, and predict 1 for Reeves, and then 0 here. So this is how I train this model. I have this classifier, the same classifier applied to every single token representation in the passage, and I'm asking whether or not this token representation is the start of the answer span or the end of the answer span. Did you have a question?
Can it be contiguous or can it be separate? Like suppose I have a different person there, actually instead of one.
So the question is, can the answer be, does it have to be contiguous or can we have separate spans? In the original formulation and in all of the data sets, the answer has to be a contiguous span. If it's non-contiguous, it becomes very difficult to use this setup to predict the multiple answer spans. We'll see how you use this at test time, and that'll make it more clear. Other questions? Wow, okay.
Is it necessary to have a 0 or a 1 prediction by the software here, or can it be something like when you use this classification, like every candidate used to have a probability, a different probability, like it wasn't like just one of them had probability 1 and the other was.
So what is the alternative that you're proposing here? Like you have a bunch of candidates extracted from the doc.
Can it be like there are a bunch of candidates start points or some candidate end points, and then we choose the better one, or is it like we have to have just one?
So the question is, do we have to have just one answer span that's like 0 and 1 or 1 and then or can we have multiple answer spans? So what I've written out here with the 0s and 1s are the targets for the classification to train these softmax layers, because we know in the data set that we're given, we actually have the ground truth boundaries of the answer spans, right? So remember when we're using the cross entropy loss, right, our target distribution is going to be the one that maximizes the likelihood of our training data. So in this case, I'm going to put 100% of the probability on the span that is associated with Keanu Reeves. So that's not the case. That's not what the actual model will predict, however, right? It will give you a non-zero probability for every single one of these spans, but we'll see how we, at test time, after training this model, use these probabilities to select the most probable span as the answer candidate. Yeah, that's a good question. So what happens if there isn't an answer in the passage? In the original squad data set, there were no examples like this, so you were guaranteed to have an answer in the document. Then they released squad 2, in which I think about half the questions did not have an answer in them. And what you basically did in that case is you add a special token to your input that's like no answer or something. and the model will have to put some probability on this thing being the start of the answer for it to be chosen. So it didn't really change how the model was used at all. But yeah, in many of the data sets, there are, all the questions are guaranteed to have answers in the passage. In some, there are questions that don't have answers in the passage, but it's pretty simple to use the same framework to solve those questions. Uh-huh. Uh-huh. So the question is, if you have a setup where you say, is this token part of the answer or not? Can you use this to handle these like non-contiguous answers? So every single token, regardless of what you do, at test time will have some non-zero probability of either being the start of the answer or being part of the answer. So if you did what you suggest, you'd have to try out all possible spans of all possible non-contiguous spans in the document to find whichever one has the highest probability, which is probably infeasible computationally, especially if the size of your document gets bigger and bigger. So yeah, and also none of the examples in any of these data sets has those kind of examples. So it would be interesting to see how to solve those, but I don't think you can use this setup to handle that. All right, one more question and then I will, I think, one of you two. Uh-huh. Yeah, so the question is basically, how do you figure out this answer span if there's, you know, like I guess many possible candidates? Let's just get into that now because I think that'll also address many of the questions that were asked. So the question really is, how do we select an answer span at test time? So it's fine during training this network, we already know the locations of the span, so we can maximize the probability of the ground truth start of the span and the ground truth end of the span in our two classifiers. But at test time, we don't know the location of the correct answer. So basically, we're going to find the span, let's call it Pi to j, that maximizes the start probability. How do I want to write this? Maybe I'll say P start I times P end j. So P start I is given by our first classifier, which is giving us the probability of any token being the start of the answer span. P end of j is giving you the probability of this token being the end of the answer span. And so, of course, here you still have a lot of different candidates to search. There are some heuristics you can use to prune the space of possible spans. So, of course, you want to exclude spans where j is less than I. That doesn't make sense if the end of the span is actually before the beginning of the span. And in most of these data sets, you also exclude spans longer than some threshold. So you might exclude all candidate spans that are longer than, say, 10 words or something like that. This threshold is usually set based on the statistics of the answers in the data set. So in a data set like Squad, most of the answers were entities or dates or numbers. So there were very few very long answers. So you can easily search for, you know, all possible 2, 3, 4 word long spans, compute the probability of the start times the probability of the end for each of these spans, and pick the highest one. So this is what you do at test time. All right, so does that make sense? Any questions?
So this one is the parameter of the model, or just the thing that we just beyond the thing that I mentioned?
Sorry, can you say that again?
So in this model, you said before that the threshold should be kind of given on the how it is.
Right.
So is the parameter in this model or somehow?
Oh, this threshold, is it a parameter in the model? Is that your? No, this is not a learned parameter. It's something you choose based on your validation set performance, like a hyperparameter. Yeah.
I don't understand. So, like maximum for all the IIT, will it not be like max for IIT? Like, would we separately find the I for which like P card is max?
The question is, won't we separately find a span where P start I is the max and a different span where P n j is the max? And maybe neither of those two indices are included in the span that maximizes this product. Is that what you're saying? Yeah, but remember that our goal here is to find a span, which is both the start and the end point, that is the answer to the question, right? So just because one token seems to have a very high probability of being the start doesn't mean that there's a corresponding token that also has a high probability of being the end token that satisfies all of these conditions. So it is very possible that the span that is eventually found doesn't have either the highest start probability or the highest end probability, but the product is the highest. Okay, so at this point, I kind of wanted to just show some results to motivate the whole pre-train and fine-tune paradigm. So we've talked about many different ways to fine-tune BERT to get it to solve all these different tasks. If we look in the paper, we can see their results table, which is quite impressive. Yeah. So if you look at this table here, this is results on the GLUE data set. GLUE consists of many different text classification tasks. So SST2 is a sentiment classification data set. NLI is, of course, we saw it before. It's a this like three-way classification problem. All of this is like paraphrase identification and so on. So you see the pre-OpenAI state of the art. So these are models that are basically trained from scratch on these data sets. And for most of these, you see a pretty huge gain in performance. Sentiment analysis is generally a pretty simple task, so the gain is like relatively small here. But you see, for instance, on this task, COLA, which is basically, it gives you a sentence and asks you if this is an acceptable grammatical sentence or not. And the sentences are pretty difficult. Without any sort of pre-training, you were getting 35% on this task. And with BERT, the large model, you're up to 60%. So this is a huge difference in performance. Similarly, you see on these other data sets also a pretty big gain, and averaged across all of the different tasks in this benchmark, you're getting a big improvement from 74 to around 82. So it shows the power of pre-training and then fine-tuning. There are also other tasks that they tried. So here are the results on Squad. This is the QA task that we just discussed. So before this, we have the model with Elmo. So we talked about Elmo and then BERT, which was getting a test F1. So we haven't talked about how to evaluate this QA task yet, but basically it's evaluated through the F1 metric of token overlap with the answer. Elmo is getting around 85, 86 F1, and BERT large is up to 93. So big advance over the previous pre-trained and fine-tuned model. And finally, one of the more impressive results was on this SWAG data set. So in SWAG, it's basically a multiple choice data set. You get a sentence, and you get 4 choices of what sentence follows this sentence. And you have to pick which of these sentences is more likely to follow the given sentence. So you can see that with Elmo, the test performance was around 59. And with BERT, it jumped to 86, and human annotator performance was similar to this. So this was a pretty surprising result at the time. Later on, it was determined that this data set might not be, all that indicative of how much linguistic information the model has learned, but it's still pretty impressive. So the interesting thing also, not only these great results, but also the fact that we're using a single pre-trained backbone model, right? This pre-trained BERT, and all of these tasks are solved with just minor modifications to the input, like adding the separator token, adding some softmax layers on the top, and then fine-tuning the model. So basically, we're transferring the same model across many, many different NLP tasks and getting great performance on all of them. That's the takeaway of this setup. So for many of you, I forgot to share my screen for YouTube people again. My bad, as usual. I guess I can do that now. But the takeaway is that essentially for your project, most of you will be using some sort of BERT or BERT-like model. We'll talk next week about things that are very similar to BERT, except they don't use masked language modeling. They switch back to normal language modeling, but are still doing transfer learning at the end of the day. So some big model gets pre-trained, and then it gets fine-tuned to solve a variety of diverse downstream tasks. All right, any questions about these results? Okay, let's see what's going on YouTube. Where in the pre-training step are the separator tokens trained? I didn't actually mention this. In the original BERT paper, there is a separate pre-training objective for the next sentence prediction task, which is where the separator tokens are used. But in the RoBERTa model, which we'll talk about next, there is no special pre-training step for the separator tokens. Turns out you don't actually need anything special for the CLS or separator tokens. The model learns how to use them during the fine-tuning process. Is the feed-forward weight matrix used to get a binary representation before applying softmax common for all passage tokens? Yeah, in the squad-style setup, you're using the same 2 weight matrices, one for the start and one for the end, to get the binary representations. There are different numbers of words and answers for different questions. How will the setup look like? It's exactly the same. If there's a 2-word answer or a 3-word answer, we're still going to apply our 2 binary classifiers to every token and then find the span that maximizes the product of the start and end probabilities that were predicted. So it doesn't impact the setup. This model only selects an answer and never generates an answer. Yeah, that's right. So this model and all of these tasks are very limited in that the answer has to be a span in the passage or the model cannot produce it. Later on, we'll look at models that can actually generate answers to questions which are more flexible. This multiplication objective could be part of the training as well, right? Forget what that was referring to, sorry. And yes, sorry for not sharing the screen. I was just going over the results in the BERT paper. So this was assigned reading, you can check it out. All right, so in the last couple minutes here, since I want to end in 10 minutes, I will go over the RoBERTa model, which is an improvement over BERT in several different ways. And it's, you know, fairly simple, all of the things that were done, but together they resulted in a pretty nice improvement, so definitely worth talking about. I won't go over the other BERT improvements that were assigned as reading, but in detail. I will just briefly mention them here. You can check out the previous year's video if you want to actually learn more about these or read the papers. But in this semester, I want to spend more time focusing on a different class of non-BERT-like models. So that's what we'll get into next week. But as far as the variants of BERT are concerned, we have several different aspects of BERT that have been, that people have tried to improve. So RoBERTa focuses mainly on pre-training improvements and more data. So BERT was trained on about 3 billion words, so it was like English Wikipedia plus some fictional data that was, I think they got it from some unpublished books, but they had 3 billion tokens. So in RoBERTa, which is the one we're going to cover here, they added more data, and they also had a bunch of improvements and simplifications on the pre-training process, which seem to make a big difference. There have been other works that try to use longer sequences during pre-training. So BERT was using 512 token long input sequences. That was the max. It cannot handle sequences more longer than that. These other models like XLNet, which is based on a variant of the transformer called the Transformer XL, can get you up to something like 900 tokens. Basically, this model combines recurrent mechanisms with transformers. So you use the recurrence, it's kind of like a memory of tokens that are far away, and you use a transformer for closer tokens. And later on in the semester, we'll cover models that extend this input size from 900 to close to 8,000 or 16,000 even tokens. So there's been a lot of progress in the architectures since BERT was developed. Then there have been efforts to come up with more efficient pre-training objectives. So one cool paper that was assigned as optional reading here is called ELECTRA. And in ELECTRA, basically, we, instead of predicting the identity of a masked word, we replace 15% of the words in the input sequence with other words. So we corrupt them, basically, instead of having, where's my example here? The students mask the books. I might create an input like the students, I don't know, hurt the books, right? And this doesn't make sense, but the model is then asked for every single token in this input sentence, is it a real token or a corrupted fake token? This objective is much more efficient than predicting a missing token's identity, as in the masked language model, because you actually have some signal at every token, is it real or fake? And also, if the fake tokens are hard enough, this can actually be a pretty challenging objective. So they showed in the ELECTRA paper that this pre-training objective of predicting whether something is real or fake is much faster to train than the original BERT model, and also results in equal or better performance across all of those tasks. Yes?
Why don't we use both, like, for the ones that we cannot predict for the
Yeah, you could, but remember that to predict real or fake, you just need a binary classifier. To predict the identity of the fake word, you need an actual softmax over the entire vocabulary, which is more expensive. So yeah, you could think about doing this for every word in the input, predict the identity, but for tokens that are real, it would be quite trivial, right? You just predict the whatever word was in the input. So yeah, that's why they went with this, real versus fake. All right, and finally, people have looked into making these things more efficient in other ways, so smaller models. Usually if people don't have a GPU or they have a very cheap GPU, it's hard to even load these models, let alone fine-tune them. Remember that if you're doing backprop, you need to keep copies of the parameters and the gradients at every layer, which can fill up your space, your memory pretty fast. So some efforts in this have been Albert, which you can also see the creative naming process here of many of these models. Albert shares the parameters at every layer, so you get a much smaller parameter footprint. There are things like distilled BERT and tiny BERT that use model distillation to go from a big model to a small model that has roughly the same or similar performance. We'll have a whole lecture about distillation later on. All right, so in the last couple minutes, I will just go over the first of these because I think it's quite instructive for even your projects if you're looking for ways to improve the performance of some model that you've built. A lot of these tips can be helpful in general as well. I'll take questions at the end. Okay, so in RoBERTa, we have a simple set of modifications. So one of the first ones is just a hyperparameter decision, train with bigger batches. And so you have a smaller number of total batches if you increase your batch size, which also means you have potentially fewer gradient steps that you're taking, when you actually update your parameters, but the gradient is more reliable. We talked about this before, and one way to implement this, even if you're using a low memory GPU, is by gradient accumulation. So in gradient accumulation, you pass a batch through your network, you compute the gradient, and then instead of immediately updating your parameters using the rule that we talked about, right, in the direction of the negative gradient, you instead then pass another batch through the model and you accumulate the gradient. So you basically add the gradient from the current batch to the one that you got in the previous batch. You can just do this for as many batches as you want. And then finally, when you're satisfied with the number of examples you've seen, then you update your parameters and then restart the process. So this is a nice hack for getting large batch sizes on kind of resource-constrained machines. It's very easy to implement, so any of you could do this, and I suspect it'll be very useful for people using things like Google Colab. So this bypasses some of the GPU memory limitations. Secondly, RoBERTa has no pre-training task for the CLS token. So I did not talk about this in detail, but in BERT, they had a separate pre-training objective for the CLS token, which was some sort of classification problem to see if two segments are in order or not. It was called next sentence prediction in the paper. They said that this was very important for making BERT good for text classification tasks, but it turns out it's not important. You can drop it and get the same performance. So this was a good simplification of the pre-training process as well. So basically there's nothing special in pre-training about the CLS token. It's just some token that's prepended to every sentence, every input, and it's not treated any differently, and it still works when you use it as a classification head during fine-tuning. The more significant changes were pre-train on more data. So they went from 16 gigabytes in BERT to 160 gigabytes, so 10 times the amount of pre-training data. Remember that in the pre-training task, basically any text will give you free labels, so you just need to collect as much raw unlabeled text as you can. This text came from the Common Crawl mostly, so if you're unfamiliar with the Common Crawl, they basically do a crawl of large portions of the internet on a monthly basis and then provide the results that you can download them. They're like, huge dumps, so you want to really do a lot of filtering on this data set and cleaning and deduplication and all of this before you actually do pre-training. So they did all of this, they got a lot of data, and they were able to see some nice results. Another trick that people have used is to scrape URLs that are referenced on Reddit. So the idea is that if someone posted this URL on Reddit, it was probably useful for explaining something or the other. I don't know how valid that actually is, but many different models have used this trick to get more like topical or informative web pages than what you would get on the Common Crawl, which is just like mostly random garbage. Yeah. And then finally, we pre-trained for longer. And so this is again a hyperparameter decision. How many iterations do you train your model on before stopping? And in RoBERTa, they used more total batches and epochs and trained for a total of 500K steps. So step is essentially every time you do an update of your parameters. So they trained for 500,000 of those. And I should mention here that so it might seem like this is just a bunch of engineering tweaks to this underlying setup to help it improve. And that is true. And you might be wondering, why didn't the BERT people try all of these things before they released their model? The main issue is that these models are incredibly expensive to run, right? If you're doing backprop for 500,000 updates on 160 gigabytes of text, you really need a huge number of computational resources. So I think RoBERTa was trained on like 200 something GPUs in parallel. BERT and all of the Google models are trained using TPUs, which normal people don't really have access to. And there were, when BERT came out, a lot of computations people did over, if I train BERT on my one consumer grade GPU, for how long will it take me to reach this performance that is reported in the paper? And it was like 1 year or something like that. So in general, a lot of these huge models still nowadays are restricted to, like, the training of them is restricted to the big industry labs. Like even, we have a pretty nice GPU cluster at UMass, but we can't pre-train one of these models from scratch in any reasonable amount of time. So hopefully that changes. We'll talk about later in the semester more work on efficient training of these models and sparsifying them and so on, but that's still the case today, that a lot of the bigger huge scale models are in the domain of industry and not normal academic researchers or even smaller companies. All right, so that's all I had to say for today. Any final questions? See you on YouTube. Nope. All right, so I will see you all next week when we'll start talking about T5, which is a text-to-text transfer learning.